Hello class, welcome to today's lesson, and we're gonna make a partial stop on subtopic 1.4. We still have something to study from 1.4, but I thought about relaying that to subtopic 1.7. I'm gonna give you the reason why when we see that subtopic 1.7. In that subtopic, we're gonna take a look at the small subject or concept that we were not seeing so far in regards to 1.4. So let's jump and let's dive into subtopic 1.5 right away. So this is the loss of exponents with integer exponents and an introduction to logarithms. So let's start, guys. First, let's talk about the following. What is the reason for exponential notation? What I mean is this, guys. Well, you have the answer right away. It's just convenience. But let me try to explain to you what I'm talking about. So, when mathematicians invented this notation, 2 to the 3, when they decided, you know what, let's write the following number, which is 2 times 2 times 2. When we have this type of number, which basically is made up of the same number multiplying itself many times, let's try to compress this or make this more economical, and let's say that this is going to be the same as 2 to the 3, or more formally, that the definition of this symbol 2 to the 3 is going to be exactly the same as the multiplication of this number in the base as many times as you have in this upper number. This number was given the name of base, and this number was given the name of exponent. Okay, and that's what it means. They decided to represent numbers like this in this compact way. Why? Out of mere convenience. I mean, probably other things, but convenience was among those things. Okay, imagine trying to deal with a number like this. 2 times 2 times 2 times 2 times so many twos. Let's say 1000 twos. You have 1000 twos in here. Okay, and um, on a given problem or on a given analysis, you need to work with this number. Okay, which I'm not gonna write down because there are so many twos. You know, nobody's gonna write 1000 twos to represent this number. We can write the three dots and that's enough and make this a specification. We have 1000 twos. So this is very cumbersome in mathematics. Cumbersome is kind of like difficult to handle. Okay, como burdo. So this is way too cumbersome, and mathematicians, being the very clever people they are, they decided to represent this type of number with the notation that I gave you, right? They said, okay, let's represent all of this number by 2 raised to the 1000. And whenever we write this symbol, what we mean as mathematicians is exactly the same as this. We have the multiplication of 1000 twos. That's it. That's all it means. So 3 to the 4, that's going to be 3 times 3 times 3 times 3, etc. That is the definition, guys. And that is the reason why people came up with this notation, right? In order to make something that takes a lot of space and a lot of memory, etc., to make it very simple to write down. If you notice, we have already seen two concepts. This is one of them. Two concepts that involve the idea of convenience in mathematics. If you remember, when we talked about numbers like this, 72 million, even though this is not a very large number, it's perhaps more convenient to write in this way, right? And the more convenience will appear when these numbers are larger. So exponential notation was this, let's say, discovered or used or adopted due to convenience, and the same can be said of exponential notation. It's just pure convenience. When people get so stressed when managing this type of notation, like they don't understand why we have to do this. Like a lot of people don't like to see these types of notation, more complicated notations, because I don't know, they are, I don't know, confused or something. They're not thinking really about how much more complex it would be to manage this number in this notation. Okay, this is not a good idea. This is a very good idea. So that's one of the reasons why exponential notation was adopted a long, long time ago. So that's a piece of history for you. It's very simple to understand why we adopted that. And now let's look at the definition, the formal definition of raising some number a to the exponent x. Definition of a raised to the x. By the way, how do we pronounce this? This is also very confusing. We can say this in many ways. We can say a raised to the x, or a to the x, or a elevated to the power of x. You see, there are many ways you can pronounce this symbol. The most easy, I think, is a to the x. It's the shortest, the most convenient one. So let's define this symbol precisely, a to the x, when a is a real number and x is a positive integer. At this point, we're going to understand this symbol a to the x only when a is a real number and x is a positive integer. So basically, we are going to discard or ignore x as being either a negative integer, okay, or a fraction. So far, we don't know. We're not going to deal with that possibility. We're going to do that a little later. So x is just a positive integer like 3, 4, 5, 6, etc. So let's define this idea. What is the definition? The mathematical definition is this, guys. I already told you, right? We're going to say that a to the x, when a is a real number and x is a positive integer, we're going to say that this symbol means exactly the same or is equal to the multiplication of a times itself, a times a times a times a, etc., times a as many times as we have in the exponent. We can say either x times or xa's. So a to the x is equal to the multiplication of a by itself. How many times? X times. As many times as I'm being specified in the exponent. Remember, this thing is called the exponent. And this number that you're multiplying by itself is known as the base. And this will be our formal definition of what this symbol means. It's this. There you go. With this definition, we're going to prove the usual or the most common laws of exponents with this definition, okay? So you may want to write it down at the moment. Stop the video, write it down, and then let's continue. Okay, a great part of this subtopic, guys, is demonstrating the laws of exponents that you already know most of them. So far, you know of all of these rules, at least. I mean, we have 4, 5, 6, 7. At least you know very well 4 of them, 4 or 5 of them. And the other 2, there you may have heard of them, but you're not so acquainted with them. Okay, in this subtopic, we're going to demonstrate them all. You're going to memorize them all. It's a very good idea to memorize these laws because you're going to be using them over and over and over, so that it's just a good idea. So let's see. What do I have in here? I'm writing, in all of the following laws, x and y are integer exponents, and a and b are real numbers. I'm being very specific about what these numbers mean, and that that's always the case when you deal about any rule or law. You need to specify what your symbols mean. You cannot take anything for granted. I'm telling you that x and y are integer exponents. I forgot it here. Positive integer exponents. I should have made it more specific. And a and b, for example, this a and this b, are real numbers. So they are whatever numbers you want. The only restriction is placed upon x and y. They have to be positive integer exponents. Okay, so we're going to demonstrate the first two laws. This one, the multiplication rule, ax times ay equals a to the x plus y, and the division rule, a to the x divided by a to the y equals a to the x minus y. I'm going to show you how these rules or these laws are demonstrated uh, very formally, very mathematically, and as homework, you're going to take the demonstration of the next three. The other two, we're going to leave them for the next class. Okay, so let's go to the multiplication rule. This is the most classic law of exponents that you know. So we have a to the x times a to the y equals a to the x plus y. This is the one that you know very, uh, very easily, or this is the one that you understand the most. So the question is this, guys: can you demonstrate why this is actually the same as this? In mathematics, we need to demonstrate all the stuff we say. Otherwise, it's not mathematics. We're not doing mathematics. So let's demonstrate this law or rule. Both things mean the same. So what am I going to use? I'm going to use my definition of what a to the x means. A to the x, by definition, means a times a times a times a times a, and so on until we have xa's. Okay, that is my definition, and I'm going to use this definition in the course of my demonstration. So let's start. I'm going to write this first. I'm going to write a to the x times a to the y. And then I'm going to apply my definition to both of these numbers, a to the x and a to the y. So a to the x, according to my definition, is equal to a times, etc. times a. How many times or how many a's do I have in here? I have xa's, according to the exponent, right? Okay. So this is all of this. And then we have a times. So I'm going to place that times. And then we have all of this, a to the y, which by definition should be equal to a times, and so on, times a. How many a's do I have in here? I have a's, according to my exponent. You see? Okay. What do I do next? I ask myself this question. I'm going to look at we have an equation here, right? I look at the right side of this equation, which is all of this stuff. And I ask myself the following question. How many a's do I have in total? Because basically what I have in here in all of this that I'm highlighting, all of these guys, is basically a repeated multiplication of pure a's. I have a times 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 a, etc. So all of this line consists of a multiplying itself a certain amount of times. How many times though? How many a's do I have in all of this total? Well, if I have x a's in here and if I have y a's in here, then clearly in total I have x plus y a's, x plus y, x plus y a's. You see? So we have the product of a multiplying itself. How many times? X plus y times, or x plus y a's. And if I have a multiplying itself this many times, then by definition, I can represent that as a raised to the x plus y. You see? I'm done. If I have the product of a, pure just a's, a times a times a times a, blah, 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 times a, how many times? This many times. Okay, then according to my definition, I can write all of this as simply a raised to the x plus y, to the many times as it's being multiplied by itself. And we are completely done. That's it, guys. We have demonstrated that a to the x times a to the y equals a to the x plus y. This is the demonstration completed. So that's how it works. You see? Okay, if there are any questions, you can ask me in a moment. Now, let's go to the second demonstration. The rule of the division. What's going to happen when we have something like this? Second law. A to the x over a to the y is going to be equal to a to the x minus y. And we're going to start this demonstration by restricting x and y a little bit. They have already a restriction, right? They need to be positive integers. Both x and y need to be positive integers. And I'm going to add another restriction upon x and y. X should be greater than y. Okay, for this particular demonstration. Later, we're going to see the same demonstration for any type of x and any type of y, like not necessarily with this restriction. But in this case, I'm going to work with x being greater than y. Okay, so let's demonstrate that this law is actually true. So, okay, again, what am I going to use? I'm going to use the definition that I have established already. A to the x is equal to a times etc. times a x times, or x a's. I have x a's in here, and I'm going to use this definition. So let's begin. I'm going to first write the left side of this equation, and I'm going to, once again, I'm going to apply the definition. A to the x is by definition all of this, a times etc. times a. How many times? We have xa's in here. And all of this is being divided by a to the y. So a to the y is by definition a times a times a times a. How many times? Y's, or y times. So we have this. We have a division of the product of a's, xa's, divided by the product of y's in the denominator. Perfect. Now what? What can we do next? Well, we can employ the law of cancellation. Remember, when we have something like this, a times b over a times c, when we have equal factors up and below, we can cancel 1 and 1, like so, and the result would be this one, right? We're gonna use this law, or this rule. Okay, so let's start canceling. I'm gonna cancel this a with this a, this a with this a, and then the third a in here with the third a in here, and the next a in here with the next a in here. So I'm gonna do that process, okay, with every single couple of a's that I can get. Okay, which of these two products am I gonna be like canceling first? Remember, x is greater than y. So I have more a's in here than I have a's in here. So by the moment I get to this last a, I'm gonna still have like I'm gonna be canceling like first with first, second with second, third with third, fourth with fourth, fifth with fifth, and so on and so on. And at some point, I'm gonna arrive at a certain a in here, and this one will cancel this one. And I'm gonna be done canceling all of this first. Why? Because I have more x's. Well, I have more, yeah, I have more a's on top than I have a's below because of this, because there are more, because x is greater than y. So okay, so what am I gonna be ending up with, guys? I'm gonna be having certain number of a's that will remain untouched in this part, right? They're gonna remain alive, so to speak, without being canceled. Now, how many a's are gonna remain alive? Well, how many a's have I canceled throughout this process on the numerator? How many a's? As many a's as I have in the denominator, right? I have canceled y a's from the numerator. So if I had x a's at the beginning and I canceled y a's, then I'm gonna be left with a number of a times a times a. How many times? X minus y. These are going to be the a's that are going to remain untouched from this part in here. I'm going to have x minus y a's. And now, if I have the multiplication of a by itself this many times, then by definition, I can write that as a raised to the x minus y, and I'm done. I have demonstrated, look, that this a to the x over a to the y is equal to this, which is equal to this, which is equal to this, which is the thing that I wanted to prove, right? I have proven that a to the x over a to the y is equal to a to the x minus y, just as I wanted to prove. So the demonstration is complete. Okay, so that's how it works, guys. It could be a little tricky. Understand what's happening. Okay, in this case, we're canceling a's on top and below, and we're gonna run out of a's in the denominator first. And in here, there are gonna be some a's remaining alive. How many a's? X minus y a's, which can be written as a to the x minus y by this definition. And that's how it works. Okay, so this is how you can formally prove or demonstrate these laws, guys. I want you to try on your own number 3, number 4, and number 5, following the same approach that you just watched me do, the same approach or something very, very similar. And be patient, be slow, don't stress, and let's see if you can handle these demonstrations on your own. Okay, I'm gonna stop it right there. Let me go back with you for questions and answers. Thank you, guys.